There is a small organ hiding behind your breastbone, just above your heart. It helps build one of the most powerful defense systems in the human body, but shortly after puberty, it begins to shrink. Healthy tissue is gradually replaced by fat, its output falls, and for decades many doctors assumed that adults could live perfectly well without it. That organ is the thymus. New research suggests it may be far more important in adulthood than scientists once believed. Studies published in 2026 have linked thymus health with survival, cancer risk, and responses to cancer immunotherapy. At the same time, researchers are developing experimental methods to preserve, rebuild, or even replace some of its lost functions. The goal is not simply to make one forgotten organ larger. It is to restore the immune system's ability to recognize threats it has never encountered before. The thymus acts like a training academy for T cells. These immune cells begin as immature precursors produced in the bone marrow. They travel to the thymus, where they undergo an extraordinary selection process. They must learn to recognize infected or abnormal cells without attacking the body's own healthy tissue. Most developing T cells fail this test and are destroyed. The survivors leave the thymus as specialized immune cells capable of circulating through the body. Some help coordinate immune responses. Some destroy infected or cancerous cells. Others prevent the immune system from becoming dangerously overactive. This training process is especially active during childhood, when the immune system is still building its library of defenses. By puberty, the thymus reaches its peak size. Then something unusual happens. It begins a process called thymic involution. Functional tissue slowly disappears and fat accumulates in its place. The organ does not completely stop working, but its production of new T cells declines. The immune system increasingly depends on cells created earlier in life and on copies produced from existing immune cells. For a young adult facing familiar infections, this may not cause an obvious problem. But decades later, the consequences become more important. Older immune systems often contain fewer naive T cells, the cells capable of responding to entirely new threats. At the same time, they may contain large populations of older, highly specialized immune cells that recognize pathogens encountered in the past but provide little help against something new. This is one reason older adults can become more vulnerable to emerging infections and may generate weaker responses to some vaccines. The aging immune system is not simply weaker. Its collection of cells becomes less diverse and less adaptable. For years, the shrinking thymus was treated almost like an evolutionary curiosity. Because most T cells are produced early in life, removing the thymus from an adult was often considered relatively harmless. But a major study challenged that assumption by examining adults who had undergone thymectomy, usually because surgeons needed access to the heart during an operation or because abnormal thymic tissue had to be removed. Researchers reported that people whose thymus had been removed faced higher risks of death and cancer than comparable patients who retained the organ. The study was observational, so it could not prove that removing the thymus directly caused every outcome. The patients were not randomly assigned to surgery, and hidden differences may have influenced the results. Still, the findings raised an important possibility. Even a partially shrunken adult thymus may continue performing valuable work. Research published in Nature in 2026 pushed the question further. Scientists examined thymic health in adults and found that the organ's decline was highly individual. Two people of similar chronological age could have very different amounts of functional thymic tissue. That means the thymus may not simply fade at the same predictable rate in everyone. The researchers also connected healthier thymic characteristics with better outcomes in people receiving cancer immunotherapy. These treatments attempt to release the brakes on T cells so they can recognize and attack tumors. But immunotherapy does not work equally well for every patient. One possible reason is that the treatment depends on the immune cells available to respond. A healthier thymus may help maintain a broader population of T cells capable of recognizing unusual cancer targets. A severely degraded thymus may leave the immune system with fewer fresh options. This does not mean thymus scans can already predict exactly who will survive cancer, but it suggests the organ may carry information that conventional age measurements miss. The The thymus also represents a larger problem in aging research. Scientists have often tried to treat diseases one at a time. Heart disease receives one therapy, cancer another, and infections another. But immune aging contributes to many conditions simultaneously. If researchers could restore part of the immune system's youthful adaptability, the benefits might extend across several diseases. That possibility has triggered a race to regenerate the thymus. One approach involves identifying signals that normally support thymic tissue. In a 2025 animal study, researchers delivered messenger RNA instructions for 3 immune-related factors to the liver using lipid nanoparticles. The liver temporarily produced these factors, which are normally involved in T-cell development. In aged mice, the treatment improved immune cell production and helped the animals respond more effectively to vaccination and cancer. The method did not literally rebuild a perfect young thymus. Instead, it attempted to recreate some of the signals lost as the organ aged. This distinction matters because the thymus is not a simple bag that produces immune cells. It contains a complex three-dimensional environment where developing T cells interact with specialized epithelial and supporting cells. Reproducing that architecture safely is much harder than increasing the level of one hormone. Other researchers are investigating growth factors, stem cells, engineered thymic tissue, and drugs that alter pathways associated with thymic decline. Experiments in animals have shown that aged thymic tissue retains some capacity for regeneration when the correct molecular signals are activated. Scientists have also discovered that the environment surrounding thymic cells changes with age. Supporting cells become less capable of guiding T-cell development. Fat accumulates. Communication between nerves, immune cells, and structural cells becomes disrupted. Inflammation and cellular damage make recovery more difficult. This means there may not be one switch that turns the thymus young again. A successful therapy might need to repair several systems at once, restore supportive cells, reduce damaging inflammation, rebuild tissue structure, and ensure that newly produced T cells are trained correctly. Safety is the most important obstacle. The thymus does not merely create aggressive immune cells. It teaches them what not to attack. If regeneration produces poorly educated T cells, the result could be autoimmune disease in which the immune system attacks organs, joints, or other healthy tissues. Stimulating cell growth could also create unexpected cancer risks. Another concern is that early human evidence remains limited. A small exploratory trial known as TRIIM tested a combination involving growth hormone and medications intended to control metabolic side effects. The researchers reported signs of thymic regeneration and changes in biological age measurements. However, the study included only 10 men and did not use a randomized placebo-controlled design. It was interesting enough to justify further research, but far too small to prove that the treatment slows aging or extends life. This is where online longevity claims often move far ahead of the evidence. There is currently no approved treatment that has been proven to regrow the thymus in healthy adults and make them live longer. Products marketed as thymus rejuvenators should not be confused with controlled clinical research. The organ's strange disappearance may also have an evolutionary explanation. Maintaining a highly active thymus requires energy, and producing new T cells carries risks. As the body accumulates exposure to pathogens, relying more heavily on immune memory may have offered enough protection during the ages when humans historically reproduced and raised children. Natural selection does not necessarily preserve every system for healthy life at 80 or 90. A process that worked well during early adulthood could become harmful decades later. Modern humans now survive long enough to experience the full consequences of immune decline. For now, the most reliable ways to support immune health remain familiar rather than futuristic. Regular physical activity, sufficient sleep, nutritious food, vaccination, avoiding smoking, and controlling chronic conditions can help preserve immune function. None of these habits can guarantee that the thymus remains young, but they reduce several pressures that contribute to unhealthy aging. The deeper lesson is that organs once considered irrelevant may still shape how we age. The adult thymus is small, partially replaced by fat, and difficult to notice. Yet it may influence how well the body responds to a new virus, whether an immune therapy recognizes a tumor, and how effectively the immune system adapts late in life. Researchers are not yet ready to turn back the immune clock, but they are beginning to understand where one of its most important mechanisms may be hiding. Behind the breastbone, above the heart, in an organ that begins disappearing almost as soon as adulthood begins.